Great. So the exercise you've just done is an example in reasoning about stocks and flows, which is the topic of today's lecture. It will be a topic which sustains us through the next couple lectures in several different forms. Because this front is kind of there, that's a little bit better. It involves concepts which are at a formal level straightforward if given sufficient time to think through the issues. They can be represented precisely given a set of mathematical formalisms that are taught to students. Formalisms in the form of calculus, in the form of simple differentials and integrals, but which can be surprisingly elusive to intuition for even highly educated people. Within this class, we're going to be talking about the representation of models using in a way that depends on, for their foundation, some of these concepts that have been probed and tested in a way in this little quiz. So the intuitions that you had to sort of work to apply in the context of this quiz will come in important in reasoning about some of the behavior we see within these models. What's really interesting more broadly is that people seem to be, as a general rule, regardless of education level and background, they seem to have rather limited intuitions for reasoning about these sort of situations on an immediate basis. In other words, they can do so with enough time and with enough thought, but trying to reason about them through their gut is often elusive, even for people who are very, very skilled mathematically and who can formalize it. So if I have time, I may talk a little bit more about this particular exercise and some of the surprising results that have been shown in other classrooms and other situations from highly educated audiences. What is to be ensured is that a lot of the reasoning you attempted to bring to bear on this situation will be very useful in the coming lectures. So we talked last time about two components of system dynamics models, sort of the two main building blocks out of which we construct quantitative system dynamics models. Can anyone remind me what those two major types of components are? Stocks and flows. Thank you. Yes, exactly. So can anyone summarize for me what is, when we talk about a stock, what do we mean by a stock?
Something stored.
Okay, something stored there. It's sort of the noun of the associated with the model in the sense that it's describing a set of things. Sorry? In kind of an inventory. It's an accumulation. So how is the stock modified? It's modified through flow. It has some initial value, some initial number of people in the store, for example. Oh my God, this guy right there is getting a leg up, but that's okay. We'll try to get that. There's an initial number of people in the store, and then there's flows that affect that stock subsequently, right? And so we don't write an equation per se giving the value of the stock at time t. Instead, it's implicitly described by the values of the flows. So we talked last time about stocks as rapid accumulation. They can be measured at an instant in time, and they are such that they don't instantly change. They change via the influence of flows, typically in a somewhat gradual, continuous fashion in any case. And I talked about them as a source of delay and a source of inertia in a system. They kind of represent the state of the system, and often what we can affect in real-world systems is the flows, And eventually that will impact the stock, but it takes time. The stock is the memory of the system. It represents the current state of the system, and to nudge that state requires sustained action, often in terms of changing the flows. Okay? So we can reduce the number of people getting sick per week by implementing, through flu, by implementing a mass vaccination campaign, or by implementing social distancing advisories and recommendations. But it takes time to end up impacting the stock of people out there who are currently ill, for example, with a longer-term illness. Okay, and we noted that in stock and flow diagrams, stocks are shown as rectangles. Okay, so we will be using some software here today, particularly AnyLogic. So if people want to grab machines here, who needs a machine? If I can get that, actually, be sure to write your name on it. Thanks very much, Seth, for delivering us. Sorry. No, we're just getting warmed up. We have a pop quiz, and they wouldn't have been useful for that. Okay, so we talked about how stocks are represented in these diagrams using rectangles like this, and then we talked about their persistent rate, but more importantly, we talked about flows, the sort of the yin of the yin-yang associated with stocks and flows. So I'll change it to stock and curve flows. And flows are the quantities that are going to be, whose formulas will be directly specified. Stocks, their value at a given time depends implicitly on the value earlier and the value of the stocks and the flows into and out of them. They vary according to the values of those flows over time. If the net flow is inward, the value of the stock rises. If it's outward, the value of the stock declines. Flows, and so we don't directly specify a formula for the value of that stock at time t. That's implicitly given. By contrast, flows, we do specify a formula for. And the value of a flow depends on what? The value of the stock, the stocks in the system. So the rates of flow are dependent on the current situation of the system as captured by the stocks, the current state of the system. We can use different terms for it. So that rate of flow out of your bathtub depends on the amount of water in your bathtub. Right? The rate of flow out of people leaving a hospital emergency room depends on how many people are in the hospital. It may not be a direct, super clear relationship, but if there ain't anyone in the hospital to leave, there's going to be no one leaving it. Okay? So it depends on it. And we noted that flows are always expressed in some number of units per unit time. Okay? So it's a rate. It's like people per day, or people per month, or cars per second on a passing on a street, what have you. And we noted that traditionally with flows, it's hard to measure at an instant in time. It has some value, which is it's hard to measure it. And often we measure it by accumulating it over a short period of time and figuring out over what period of time did we accumulate that and how much do we get as a result in the accumulation. Just like I argued that, if you want to figure out how quick water is coming out of the well, you figure out, say, how much water you get in 1 minute of pumping the well, how many liters of water do you get, and you can figure out how many liters per minute you can get out of that well. Okay? So here are the flows within our stock and flow models. The stocks depend for their values on the flows, and that's an implicit relationship. The flows depend for their values on the values of the stocks at the current time, and that's an explicit relationship. Okay, we give a formula for that flow. So I want to go through a little exercise here. So I'm going to throw out some quantities and ask, are these stocks or flows? When we quantify them, would we be quantifying them as if they're flows or as if they're stocks? So births, Sorry?
Flows.
Flows, yeah. There are so many babies born in Saskatoon within the past year, right? Again, this reference to sort of per year kind of gives it away. And it would flow into, say, a stock associated with the size of the population, right? Profits. My company has high profits. Our profits are $1 million. What's missing there? The timing. $1 million per day. Wow, man, you folks are going to be coming up after me. You get a job, right? On the other hand, if it's $1 million per million years, you might be running away from me, as if you're not already. So there's a big difference there. We need to mention something about the unit of time involved.
Professor?
Yes?
Couldn't something like profits be either a stock or a flow depending on what kind of system you're trying to model?
Sorry?
Couldn't something like a profit be a stock or a flow depending on what you're trying to model? Because, for instance, the profit might be a flow into what, how much liquid cash you have.
Yes.
At the same time,
yes.
It might be the stock that your other, everything else on your balance sheet is flowing into.
So you're asking a question which does indeed come up, and at a conceptual level, you are correct that, and you'll notice how I phrase this, that the fact that because it is per unit time, we have a situation where probably it's operating as a flow, at least at some place in the system. Could a stock be something measured per unit time? The answer is yes in some cases. And physicists often see this immediately, right? Because you have position, velocity, acceleration, right? And from the point of view of acceleration is maybe the flow, and velocity is the stock. And from the point of view of the position, the flow is associated with the velocity. In practice, within the models, you will often see outside of the physical domain, this sort of situation is less common. It does sometimes happen, but it's much less common than you'd think. And often within a model, if we're thinking about characterizing situations like we're describing here, it's a pretty good intuition for classifying them. How do we represent our model? But it is not, it's more a heuristic than an absolute distinction. And you are right, you can have a situation where something simultaneously operates in one part of the model as a flow, and another part it's serving as a stock. And we have, essentially, conceptually, we have second derivatives there. Right? Yeah. So you are right. I am trying to simplify things up front. Okay. Okay. So how about arrests? Saskatoon had 300 arrests. Flow, probably an indication it's a flow. We had number of incarcerated individuals. Stock. Pretty clear it's not a flow for most of our uses. Okay, the number of patients in a hospital. Stock. Yeah. And I put these last ones in just to get at this subtle issue there. Okay, so let's talk about the net impact of a flow on a stock. So suppose here that we have a flow whose value is consistently 10, maybe it's people per month, right? 10 people per month presenting with diabetes. Then we have stock of number of people that initially starts at 0, and as each successive month, if this is the only flow, it's a flow in over time, the value of the stock is going to rise linearly, right? You folks would have seen that in calculus as the integral of a constant dt, right? And turns into a linear factor, so we get a value alpha times t as the value plus some constant. In this case, the constant is given as 0. It starts at 0. Now, suppose we lowered this flow rate to 5 per month from 10 per month. This is purely a flow into the model. And what do we expect to happen if we were to lower it to 5 per month, say in the middle of this trajectory. So right in the middle here, what would you expect to see if we lower it from 10 per month to 5 per month?
The slope would be cut in half.
Okay, the slope will be cut in half. So it'll still rise. The flow goes down. And you notice that this is a little bit confusing because it's not on an axis that goes from 0 to 10. I apologize about that. But what happens with the stock is it's risen to this point with a net inflow of 10, and suddenly we've changed it to be a net inflow of 5. It still rises, right? But it rises less quickly, right? Okay. So here, a big change in the flow, sudden change in people's habits, for example, has an impact on the stock, but the impact is not immediately felt. There's no giant discontinuity with respect to this stock when this flow changes. The value of the stock doesn't suddenly drop, suddenly shift to an entirely new value. In fact, it's a continuous process, and it changes, and over the longer term, it becomes a larger and larger change that's affected, but it's not a discontinuous change. It doesn't immediately jump in a pronounced way. Do people appreciate that? You change the flow suddenly, which is often what we can try to do in life, and the stocks respond, but they don't respond immediately. Even if you're wildly successful, the dreams of epidemiologists everywhere, halving the rate at which people get diabetes, it's going to take a while before you see those changes play out in a really pronounced way within the population. Okay. And at a deeper level, when it comes to states of systems, often causal processes do not affect big changes instantaneously. And if we're looking at feedbacks by their nature involve a stock and a flow. We have a situation, you may recall, when we have a feedback of a situation where some variable A is associated with some pathway, maybe through variables A, B, C, etc., which eventually leads around to impact A. So an increase in A leads to a cascading series of effects which ripple around and eventually push back against A in the case of what sort of loop? Push back against that change in A, that if we increase A and they ripple around and push back against that increase, we call it a what sort of loop?
Negative feedback.
Yeah, negative feedback or balancing feedback, right? A regulatory loop. It kind of keeps it in balance. We perturb it, we push it, and it pushes back at us, right? Yeah, a negative feedback loop. That, by nature, that loop involves a stock and a flow. So there's always a stock and flow involved in it. And that initial change may be affected, associated with the stock, and it ripples around to the flow associated with, to one or more flows associated with the stock to push back, to drain that stock more quickly, for example, to counteract that initial increase. So loops within the context of stock and flows are always going to involve a stock. The stock is the state of the system. It's the current situation. And that's where the delays occur, moreover. So this loop is going to play out, and it's going to operate by changing the state of the system. So there may be many steps along it that involves flows, but at some point it's got to nudge the state of the system. Okay? The change is a change occurring in the current situation, the current state of the system. So all causal loops involve, one change stock. The state of the world has to change as part of that process. Absent a stock, the loop will be instantaneous. It's the stock that sort of leads to the change in things. So we have, for example, population and bursts per year, and here we have a stock on the right and a flow on the left, right? And it does ripple around to affect this stock. In this case, it's a positive loop, which we call a reinforcing loop. It's associated with instability. And but that loop includes both stocks and flows, and it has to. Okay. So that was a little bit there. We're going to develop some further intuitions involving stocks and flows in just a minute, but I'd like to present you with a few of the other types of variables you will see in system dynamics models, bearing in mind, ladies and gentlemen, that these additional sorts of variables are less fundamental. They are mere conveniences, mere notational helpers, rather than fundamental building blocks at a conceptual level of our model. They are things that we represent almost for software engineering reasons and help us understand models for human reasons, reasons in the human theater, rather than per se issues that are mathematical. And at a mathematical level, they fall out of the system. Okay, they're sort of beside the point. They don't alter the mathematics of the situation. So the most important of these is something called an auxiliary variable. Okay, these are convenience names that we give to certain concepts so that we can easily reuse them and so that we can parse more easily conceptually what's going on within this model. And typically they're defined in terms of stocks and flows, either directly or indirectly through other auxiliaries. Okay, and they're critical for model transparency. Let me give an example here, okay, to give you a sense, because it's easy to fool yourself with abstractions. So here we have our model of stocks and flows down here, and these are really, delineating the fundamental governing properties of the system. But those governing processes are occurring through the help of a set of, you can think of them as helper variables, convenience variables. Variables that at a philosophical level and a mathematical level fall out, but are useful names. An example here would be the prevalence of infection. That's a shorthand, a brief name that we give for a certain expression. And what is that expression? Well, it's the number. Well, could anyone tell me from health background? If we talk about the prevalence of infection in this population, what sort of expression would that be? Can anyone give me the formula?
Total number of infected persons
Yep.
in a specific population at a specific point in time.
Good. And that's the total prevalence. If we want to express it as a fractional prevalence, it would be the number of infectious people divided by what? The total population. So susceptible, infectious, and recovered. Or, even better, we might, here we would, so that's what it boils down to. But in order to express that, rather than writing explicitly every time we need to refer to that, writing infectious divided by susceptible plus infectious plus recovered, we could write that formula every time in terms of the stocks and flows, right? These are stocks, and we could write that out, right? But rather than doing that, it's good as software engineering, among other things, to give names to things. Some of you have heard me opine about this, maybe more than you'd like, in other classes and other things. But this is this setting, and at this point in time, and I'm going to opine about it again. Giving names to things is extremely important to help understanding. And so what we do, rather than just every time we need to refer to prevalence infection, just substituting this formula, infectious divided by susceptible plus infectious plus immune, we instead give it a nice name. We call it prevalence of infection. Okay? And we give the total population a nice name called total population, and that's susceptible plus infected plus temporarily immune. It's just a name for that expression. It's a name for that formula. It's nothing more. And at a mathematical level, when we go to analyze a system like this, those names disappear. And we're left with the underlying formula. But it's convenient, because maybe total population is used many places in the model. Maybe we refer to it in many different places. And maybe it's just easier to read that and know what it means than it is to look at the formula and know what that means. Maybe, moreover, we plan to extend this model by adding additional compartments, by adding additional components here. Maybe asymptomatic infectious and a symptomatic infectious compartment. And by having one place to go to for total population, it's easier to remember, rather than going everywhere in the model where we have susceptible plus infectious, temporarily immune, all three added together, and remembering to put this in, we can just refer to total population and just change it one place. If we add a stock, we just change total population in one place rather than many places in the model. So giving names to things like total population, like prevalence of infection, is handy. Okay, it's handy. We can use it as a shorthand for the underlying expression, the underlying formula. Okay, we often will give names to these quantities, and moreover, we'll give names to constants that we use, or to time series that we refer to. So we'll give a name, for example, as a model constant to some assumption about how quickly people recover, how long they stay sick. Okay? We'll see how this functions in the model in another probably 2 lectures, and we'll see this loss of immunity delay, how that's represented. But fundamentally, these are numbers. But those numbers, rather than just looking at a formula which says 2.3, it's nice to give it a name, and it's nice to give it an explicit unit. So we know it's in days, or we know it's in months. And so we give it a name, say it's associated with the unit, and the software can reason about those units, see if they're consistent, etc. Okay? See if it's dimensionally homogeneous, as we say. So giving things nice names, whether it's numbers or whether it's formulae, is good practice. It's good practice in all areas of software engineering, and modeling is one of those areas. It lets you know what that means, what this number means, where it came from, documented source, etc. Okay, I think I'll skip this, but I will just note that these models come in various shapes and sizes. Some models involve a single population divided up into different categories. Other models will involve, for example, many populations or many types of things circulating in the same model. This is a model we have of West Nile virus here in Saskatchewan, and we have a portion of the model devoted to mosquitoes, a portion of the model devoted to birds, and a portion of the model devoted to humans. And naturally, they do not mix, Kafka aside. Here we have mosquito population moving between a set of compartments, a set of stalks. We have bird population between a set of stalks, for example, juvenile birds up here and adult birds down here, etc. And they move within each of their own domains. We could have similar parts of models associated with costs, accumulated dollars that have been spent, and other quantities that are of interest. Okay. So those are some comments on some basics with stock and flow models. Every time we'll fire up AnyLogic in just a minute. In fact, may I suggest to you, ladies and gentlemen, I'd like you to preload your AnyLogic so when we need to get going, we can do so in a jiffy. Okay? I like to use terms that are out of favor. Okay, so I'm gonna start up AnyLogic here. Okay. While that's loading up, and while yours are loading up, and it will take a few minutes to get there, I'd like to talk a little bit about how these two types of diagrams we've seen, causal loop diagrams and stock and flow diagrams, come together. Okay. They're often combined in what's called a system structure diagram. In fact, I commented on this last time when I was going over one of the models sent by one of the students for this class. Fundamentally, we have a notion of a system structure diagram that combines sort of best features on the one hand of causal loop diagrams in the form of labeling the link polarity, labeling the loops present, and on the other hand, stock and flow by virtue of the fact that they distinguish stocks from flows. There's a very important reason for this, for building such diagrams. They provide insight beyond what one would normally find in either diagram in isolation. In a way, they're a situation where they're greater than the sum of the parts. So what sort of extra benefits do we get? Well, compared to a stock and flow diagram, the benefits are modest but significant. We have an idea visually for each of the connections about the polarity associated with it, and we can quickly spot the loops involved. And I'll come back to some of these loops in a minute. Just a high-level point there. So we can spot where the governing loops are. And again, one of the reasons we highlight these loops, whether they be reinforcing, shown here with a plus, or balancing, governing, shown with a minus, one of the reasons we highlight those is so that, for a reason such that, because they govern largely the dynamics here. And the operation of the stock and flow model, in fact, will play out in a way that involves shifting loop dominance among these loops. We can understand what is happening, ladies and gentlemen, within this model in terms of these loops. And there's software tools that will actually visualize what's going on, saying, for example, this loop here is dominant, or this loop is dominant, and this one is now becoming dominant, and showing how the model operation overall is playing out across the loops. And that's useful. There's no question that's useful. So we have some additional insights that stand out and strike us looking at a structure diagram compared to a stock and flow diagram. But ladies and gentlemen, it is more fundamental. The benefits conferred are more fundamental if we compare a system structure diagram on the one hand against a causal loop diagram on the other. Distinguishing stocks and flows within such a diagram sharpens the semantics involved of the connections. So a quantity that was merely shown as a link within a causal loop diagram is now often distinguished, for example, as a flow within a stock and within a system structure diagram. So, for example, the relationship between infections on the one hand and susceptibles, we'd expect to see that within a causal loop diagram. Could anyone tell me the polarity associated with that relationship between infections and susceptibles? What polarity would that hold within a causal loop diagram? So if we had infections on the one hand, and we wanted to have a link to susceptibles, ultimately there's a pathway around the other way, but we wanted to put in the link in a causal loop diagram between infections and susceptibles. If I will ask you to redraw this as a pure causal loop diagram, with what polarity would that be associated? Negative, because, and help me, give me the story as to why it's negative. It is negative, and why?
As infections increase, keeping other things constant, the number of susceptibles are going to decrease.
Compared to the value it otherwise would have had. Yeah, that's right. So if we have more infections going on, all other things being equal, there's going to be fewer people who remain susceptible, right? Because those infections are occurring to susceptible people, and so there's going to be fewer susceptibles remaining, right? So there's actually a negative length there. Now, the semantics of that length, though, are not clear. In other words, if you change infections, for example, how quickly does it affect susceptibles? Is it an instantaneous relationship? Well, doubling infections, halve the number of susceptibles, for example, it's not immediately clear. If you make it a stock and a flow, infections are draining susceptibles, you know something about the semantics, about the underlying dynamics that's much more substantive. You know that, okay, increasing infections will lower susceptible, but it's not going to be immediate. It's going to be draining it, and it's going to initially be no difference in the number of susceptibles, and then it will grow gradually more difference, just like we saw earlier. So distinguishing stocks and flows helps us recognize some of the more textured nature, helps us put more information in than we could have packed into the causal loop diagram by itself. Moreover, we can capture things such as conservation properties. surely dear to the heart of many physicists in this room. What, ladies and gentlemen, here is being conserved? In this diagram, where is there conservation to be found?
Number of people.
Number of people. We are simply shuffling people between these different stocks, right? And that's not immediately obvious from a causal loop diagram that simply links them up with, relationships. But it is true here. Infections move someone from susceptibles to infectives. And that wouldn't be obvious if we simply had a link from infections to susceptibles with minus polarity and a link from infections to infectives with a what sort of polarity would that be? From infections to infectives, in other words, infected people, people who are capable of spreading the infection. Infectious people would be a better term. What sort of polarity would be associated with that in a causal loop diagram? Positive, yeah. For a second, I thought someone in the hallway was answering the question. Surely they heard it. So here we have a minus and a plus from infections to susceptible. It's a minus polarity. From infections to infectives or infectious individuals. In other words, it's positive polarity. But there's no notion of conservation here, that infections bring someone from susceptibles to infections. That conservation is conveyed visually within the context of a stock and flow diagram. So stock and flow diagrams, if you can label things with stocks and flows, it adds extra semantics to things. It says what the state of the system is, what changes the state of the system in the form of flows, what might be expected to instantly change, what things might take more time, be associated with delays, associated with nudging stocks, etc. So these sort of system structure diagrams are helpful, and you can use them to diagram out situations that are both qualitative but have this extra level of sharpness associated with flows. Okay, this is from software engineering showing different states of bugs. If people had seen me in 371 today, they actually would have seen that diagram in a separate context. So let's talk about some stocks and flows, ladies and gentlemen. For example, in the software developer area, we might have stocks associated with different types of developers. So there's rookie developers and seasoned developers. Jack Homer is a very nice model showing sort of the effects of training on the dynamics of a software project. As a project hires new developers, they come in as rookies. They come in as people who need training. And that takes the time of the very seasoned, the very highly skilled developers away from developing and training these new people. And that can often lower productivity in the short term. There are flows associated with developers, flows associated with hiring, people leaving the company, quits, and people being fired, and people going on leave of absence, and other forms of layoffs, right? So we have stocks and flows affecting developers, but more fundamental, well, I don't know if I'd say it more fundamentally. Those are actually key, but they're tied up with, those dynamics on the human resource front are tied up intimately with dynamics on the front associated with project workflow and work quality, the productivity and quality associated with the system. So, for example, you might have stocks associated with the amount of work planned, the amount of work you've already accomplished, work that's been discarded because it's needed to be reworked because of, say, a requirements change in the needs. It may be associated with stocks associated with fatigue. People work long hours, they get fatigued, and that ends up affecting the quality of the work that they've done, and therefore the number of defects within the system. So you might distinguish defects, for example, within the system, perhaps even as to type, whether they're requirements defects, design defects, coding defects, and key processes like testing are associated with flows. A testing would be a flow from, for example, undiagnosed defects to diagnosed defects. And by making it diagnosed, by diagnosing a defect within our system, by recognizing a failure within our system, we could then start to work to identify the fault behind it and fix that fault. So a lot of the processes that go on within software, whether it's testing, whether it's development, peer review, training of new developers, various Q&A processes, they can be represented within a stock and flow context. And you note some flows down at the bottom here. And there's some wonderful models for those interested from computer science background, software development background, of the software development as illustrated using models, capturing the dynamics we see in real-world projects using simulation models. And they can be quite explanatory for why we see certain effects, like Brooks' law. Adding new people to a late project can make it later. Adding more people to a project that's already behind can make it even more behind. Now, so those are some stocks and flows, and I have a variety of other types of stocks and flows I could go into on the health side, but we've seen some health examples, and I could share some slides with those who are interested in additional ones. Okay, so let's talk about a fundamental principle at issue here, though, which is the principle that structure shapes behavior. This is a statement you'll frequently hear within the system dynamics area, that the structure of a model, the arrangement of stocks, the flows between those stocks, and the feedbacks associated with the system, that fundamentally defines the behavior of which that model is possible and that system is possible. The fact that there's sort of a way that things work in terms of the underlying state of the system and processes operating on it tells us something about how a system can behave. And by looking at a model in terms of stocks and flows, we can reason about how it could behave. We started to see some of that when we were talking about causal loop diagrams and talking about how reinforcing loops are associated, for example, with divergent behavior and balancing loops with convergent behavior, with moving towards an equilibrium or to oscillatory behavior if there's a delay. But more deeply with stocks and flows and the connections between them, particularly feedbacks, we can often recognize the fundamental drivers for why a system behaves in the way it does. A key component of this is nonlinearity, and we'll see some models soon which exhibit pronounced nonlinearity, which means that the behavior of the model is very different from the behavior of any one of its parts. And in fact, it requires us to use numerical methods, computers in short, rather than explicitly solving it in what we call closed form, giving a formula for how the system behaves. For nonlinear systems, for many nonlinear systems, we do not know of a way to derive a formula for that system in closed form. We can't give an expression for how that system will behave. Instead, we have to simulate it out over time in a step-by-step fashion. Okay. So the general perspective here is the stock and flow structure of the system, including the feedbacks involved, basically determines the qualitative behaviors that a system can take on. The systems that we'll be working with over the next few weeks each have their characteristic behaviors. And we could change parameter values over wide ranges, but we'll still see behaviors that are of certain characteristics. Just like a slinky. If you've ever played with a slinky, it has certain behaviors that emerge from the structure of that slinky. It tends to oscillate in certain ways, and you can shake it and move it around in different ways, but it's going to excite those same, as we call them, normal modes, those same basic underlying patterns of behavior over time. And these stock and flow diagrams, like the systems they describe, have certain characteristic behaviors, and our interaction with them are going to excite those behaviors. And if we understand those behaviors well enough and can anticipate them, we may be able to accomplish what we're trying to accomplish with those systems much more effectively than if we're just butting heads or working at cross purposes with those behaviors. So the idea is, by representing the structure, we can reason about a system's behavior, we can reason about its possible behaviors, and we can identify ways to manage the system most effectively by anticipating those behaviors and realizing what we can do to adjust them to be appropriate for our needs. Okay, I'd like to talk a little bit about flows, and hopefully we'll then dive into a little bit of modeling with these using AnyLogic here. Okay, so here we have a situation where we have a flow in of, a flow of mortality, so a death flow associated with 10 people per month, and we have a number of people developing diabetes of 15 people per month, up to time about 70, 75, and after that it's 5 people per month. So situation is a little bit similar to the situation we saw earlier, but now we have an inflow and an outflow. The blue is the outflow, the red is the inflow. Ladies and gentlemen, what will be the result over time? What would we expect to see over time in terms of the value of that stock? At a qualitative level, what would we expect to see?
It's going to increase steadily.
Okay.
Up until that sudden drop in
Yes.
the incident cases.
Yes.
After the drop, it's going to decrease steadily.
Okay. And very good. Why will it increase? Can we sharpen the term steadily, first of all?
At a constant rate.
At a constant rate. It will increase linearly and in a line-like fashion, right? At a constant rate. It may start, notice we haven't specified the initial value, and that's really a little bit beside the point, because it will rise at some fixed rate, and the initial value will determine whether it's rising from a higher initial point or a lower initial point, but it'll rise at this fixed rate until 75, and why does it rise? It rises because of what fact? The inflow is greater than the outflow, right? So it's rising. And why does it decline after 75? Because the outflow is bigger than the inflow, or the inflow is less than the outflow. You could phrase it either way. Good. So we see something like that, right? And again, the location of this green line is somewhat arbitrary, the initial starting point of it. It's in the null space of the differential operator, for those who like to speak in more formal terms. So it's just the constant added on when you integrate something, right? And it could start lower, it could start higher, but in all cases it will go up with the same slope and then decline with that same slope. It would just be moved up and down, right? Depending on how many people were in that stock initially. Suppose we have these flows. What do we expect to see then? So now, again, the blue is the outflow. The red, ladies and gentlemen, is the inflow. What do we expect to see then? First of all, when will the stock have the greatest value? At what point will the stock hold its greatest value?
The second time the red crosses the blue.
A fine answer. And a worthy one. And a true one. Why is that?
That's when the stock starts to decrease.
Okay, that's when the stock starts to decrease again. So before this point, when is the stock increasing? When is it decreasing?
Increasing when red's above blue.
Okay, good. So it's increasing for this area. Initially, what is it doing here? Decreasing, and then what's it doing at this very special point? Whoa! What's it doing here? Hold it in here. So it's been decreasing initially, and then it holds steady and then starts to rise, the value of the stock. What's it doing at this point? What distinguishing feature? Is it at its highest value? Is the value of the stock at its highest value here? No. But this point is distinguished in terms of one characteristic. What what is the notable characteristic about the stock? If we were to describe something about the stock as notable at this peak in the red, what would that thing be? It is doing what?
Increasing the most.
It is increasing at its fastest at that point, right? Because this gap between inflow and outflow is the largest, so it's going to be rising the fastest. And in short, the net flow is biggest that it's going to be, and then it decreases down. And then, so what decreases down here? This inflow. But what is the stock doing all through this period after that peak? It's still increasing. And this is the point where it stops increasing. So its highest value is in fact here, right? Okay, so when is it at its lowest value? When is it at its lowest value? We said its highest value is here, and that's correct. When is it at its lowest value?
At the end.
At the end. Why is that?
Because the gap between the inflows and the outflows.
So it's true it increased here over this, and so the two candidates would probably be here, it's at its lowest value here, or it's at its lowest value here, because, right, initially it went down, and so it could be at its lowest value here, or it could be here, but the area under this, the number of people that left during this period, given this giant gap here, is much bigger than the number that came in here. And so, it's true this value was lower than its subsequent value. It's gone up a lot since then to here. But this brings it down to an even lower level because of this persistent gap. More and more people are leaving. And so a lot more people have left here. And the value of the stock is lower here than it was here, right? So we see something like this. And naturally, it's curvilinear. It's parabolic because we're dealing with the integral lines, right? So here we see this initial decrease. It flattens out when the inflow equals outflow. In other words, the net flow is 0. And then it starts to rise, and it reaches its maximum value here. But again, it flattens. And then we have a decrease, and indeed the minimum is there. So that's good. That's good. Okay, and I gave you this little exercise. We basically asked you to exercise that theory. So here's the shocking factoid. So they give this quiz to engineering grad students. To MIT grad students who are from all around campus. Many of them from business school, but have had engineering backgrounds. And questions 1 and 2 on this quiz, most people get correct, 96 to 95%. During which minute did the most people enter the store? You can read it directly off there. During which minute did most people leave the store? You can also read that one directly off. It's just a matter of graph reading. And those two questions basically help us understand, do people know how to read a graph reliably, right? Are they in a situation to read a graph reliably? But questions 3 and 4, interestingly here. Questions 3 and 4. During what minute were the most people in the store? And then during what minute were there fewest people in the store? People's intuitions on that are off. And fewer than half, in both cases, this population. Highly select population. So people admitted through an extremely competitive admission process, and I believe even getting into this course, you have to go through a raffle or what have you, but you're dealing something with a very, very talented group by and large. Most people get it wrong. During what minute were most people in the store? Well, you have to reason about, okay, we've got entering versus leaving, and essentially we've got a net flow in, which is positive during this early period, right? We have more people coming in than leaving here, so it's net flow in, so it's going to be rising up to this point, right? And then we have leaving greater than arriving, so it's going to be decreasing after this point, right? And the same sort of reasoning, and so in terms of the most people in the store, from whatever the initial value is, it's rising up here. here it's going to be bigger than the initial value, and it's going to be bigger than any value after it because more people are leaving than are arriving there. So this has got to be the maximum. And then the fewest people, you have to reason once again, the area under this versus the area under that, right? But it is surprising in a way that people's intuitions mislead them. And actually quite a few will say that, the number in the store, it's at its maximum at this point, when this is at its maximum, which is far from the case. People are just not very good at intuitively, immediately sort of seeing this. They have to reason through. And given enough time, they can. But often in our daily life, when we're dealing with complex systems, when we're trying to make decisions in the midst of a complex process, in the midst of a meeting, we don't have time to sort of sit down and really think these things through. And whether it's when we're dealing with bug reports, number of being fixed, the number of being reported, or other factors, we end up making lousy decisions based on intuition. And ladies and gentlemen, this is where computers can help us. Because computers are awfully dumb still in many areas, but one thing they can do pretty darn well is to do bookkeeping for us and to integrate things up over time like these sort of models. They can solve things with lots of moving parts that we find really hard to keep straight in our heads. We're really good at recognizing some things, recognizing faces, etc. But when it comes to reasoning about this sort of situation, a computer can outdo us any day. You can simulate that. Okay. So let's talk about building something up here. We're gonna we've been talking about stocks being changed by flows, but thus far we've used constant values for flows, which are helpful for developing some intuition. But in the most part, flows depend on what, ladies and gentlemen? They depend on the value of a flow at a given instant in time will depend on the what? The value of the stocks at that same point in time. So we're going to see if we can capture this. Okay, so I say create this in Vensim. I thought I had changed that to create it in AnyLogic, and we'll do that. Ladies and gentlemen, you have AnyLogic. AnyLogic is fired up. Let us use the closing minutes of this session. We have about 10. And let us, ladies and gentlemen, let us model. Okay? So I'm going to go to AnyLogic here. And it started in a fashion that's shown here. I'm not sure. Oh, okay, that's GIMP. Okay, fine. So here I just called up AnyLogic. Let me make sure the remote person you still see screen. So here we have AnyLogic, and I'm going to go create a new model. File, new model. Okay? And we're going to call this first order delay. Okay? If you want, you could call it my first order delay. First order delay. Okay? And I'm going to put it into a certain folder so that we can preserve memory of this. Okay, so here we go. Right. Here we go, and we'll put it into this class folder. There we go. Okay. So let's go create this, and we'll say finish. So I just am creating this model, and this is going to be an exercise that we're going to go through many times later in the term, so it's worth lending yourself a bit of familiarity with it. Okay? So down at the bottom here, if you have I have multiple projects, you may not. We have first order delay. And first order delay, initially in it, it has main and an experiment. Okay? And we're going to operate purely within main here. So double click on main, and there should be a canvas that comes up for the main. Do you folks see that?
Yes.
Yeah? Okay. Okay. I'm going to start to bring a TA here, perhaps, to help me out. Okay, so now what I'd like to do is go in there should be a window called Palette. And if there's not, you could go to View and choose Palette. So it's possible it will be hidden. And you may need to do View and make it visible here. Occasionally, it's kind of minimized off to the side. folks may recognize this environment. What is this environment we're operating in? What does this remind you of? Of what does this remind you? Eclipse, yeah. So we can do restore and that comes back. And we could double click on it and make it full screen and good stuff like that. But for now, we just want this palette. We want to go to System Dynamics area and we want to go create a stock. Okay. And I have a stock called stock. I think I'm gonna call it people with virulent infection. Okay. It sounds more interesting than stock, I think, at least to me. So I'm going to drag in from System Dynamics. I dragged it into the canvas here, and I'm going to call it people, but Java is a harsh taskmaster, and I can't use spaces, so I could do underbars, people with virulent infection. Note the underbars are underbars and not, ladies and gentlemen, dashes. Java does not like dashes in identifiers. Underbars are copacetic, but dashes are not. Okay, so be sure to use underbars. And I've added this stock in. I'm declaratively specifying a model here that's going to be able to run. Okay, so we just added that stock in. Next, ladies and gentlemen, I would like to create a flow out of that stock that's labeled deaths from infection. So we're going to drag in here a flow, and we do so by dragging from the System Dynamics area, and I drag it and position it so that, because it's a flow out in this case, it's going to be flowing out of the stock, so I'm positioning it so that its left side there is flowing out of the stock, okay? And it's letting me name that, and I'm going to say deaths from infection, okay? And you'll notice these names are a little bit overlapped, so I'll see if I can move them around. So we're going to have this deaths from infection, people with virulent infection, okay? So we can move the names around by clicking at the right point, and particularly if you click on the stock, for example, you can easily move its name so it doesn't conflict. Okay, so we've declared this stock, we've declared a flow. Can we run this model now? Sorry? Why not?
Because there's no specification of how much depth.
Good.
What is the stock?
Good.
It's not going anywhere either.
Yeah, we haven't given it enough information about where it's coming from even, right? What's the initial situation? What do we have to do to specify the initial situation? When I say situation, what does that make you think of? State, the state of the system, the stock. So I've got to specify what for the stock? I need to specify its initial value. Do I have to specify its value at every point in time? Most emphatically, I need to specify its initial value. Because after that, its value will be determined by what? By the flow, or flows in general, but in this case, it's one flow. So ladies and gentlemen, click on the stock and specify its initial value to be 1,000. Initial value of 1,000. Could we run the model now? Why not? What's missing? Okay, we haven't specified this precisely enough to allow it to be simulated. We haven't specified the dynamics, the semantics, the meaning of this flow specifically enough to allow it to be simulated. Could it still be useful to show someone this model? Just to kind of diagram what your how you characterize the situation? Yeah, it can have a little bit of value. You know, we think of people with infection and then there's deaths from infection. Yeah, that can be useful. And in some contexts, you show models that are not yet fully grounded, I should use that term cautiously. We use models that are not fully specified, not fully quantitatively specified. But here, we are seeking to do so. We are leaving the qualitative and going to the quantitative here. So to specify this, we will need to specify, in fact, a formula for it. So ladies and gentlemen, what I'd like you to do is we're going to do two things. First of all, we're going to create a variable, a so-called auxiliary variable, constant, called mean time until death. So it's actually a constant variable, but but in this case, we'll let it just be specified here with an auxiliary, and it will recognize it's a constant. So we drag it in from system dynamics, and we'll call it mean underbar time underbar with underbar infection. The Java compiler is unforgiving. Even one forgotten underbar can lead to grief. So mind your underbars. Okay. So we've placed this mean time with infection. And what I'd like you to fill in, excuse me. Oh, man. Well, mean time with infection, that's fine. Or you could call it mean time until death. And I'd like this to be a value of 10. Okay? 10 time units. We can go, we'll go see another time. Time is a ticking. And we'll go see another time where we specify is it days or years or what have you. Right now, we'll just specify it as 10 of the current time units. And then, ladies and gentlemen, we need to make this clear and to clarify it as a visual artifact. We want to make it clear that deaths from infection depend on mean time with infection. And we do so by putting a link in. It depends on that. It's modified by. So we drag in this link, and we link up mean time with infection to this deaths from infection. You'll notice that when I drag these links around, it's important that they dock properly. They turn green to indicate that it's connected. It's truly connected. It's not merely close. This isn't horseshoes. It needs to be directly on it. Okay? So mean time with infection. And the other link that needs to be there. What other link needs to be there for this to be at all meaningful? Surely, deaths from infection, it needs to depend on one other thing in this model. What is it?
Dead people.
Well, okay, it yields individuals who are dead, but in order to operate deaths, in order for deaths to occur, there have to be what? People to die, right? And so surely, if there's nobody left with a virulent infection, if there's nobody left as a candidate to die from the infection, there's going to be nobody dying. So we need a link from what to what? Just expound upon my statement. We need a link from people with virulent infection to deaths from infection to capture the fact that deaths from infection has to depend on a number of people with virulent infection. We know that because if people with virulent infection is 1 billion people, we're going to have a lot more people dying than if there's 0 people to die, right? It's got to depend on it conceptually. So we're going to drag in a link here from people with virulent infection to, oh, look at that. It just nicely linked up. Now, maybe some of you aren't so lucky with how you positioned it. So I will pretend that I had it dragged here, and I'll just drag this guy up to that point. Okay. So here we have a situation where we've shown visually that deaths from infection depend on these two things. People with virulent infection mean time with infection. It depends on both. If people stay with their infection for longer, in other words, it takes a longer time for it to be lethal, there's going to be fewer deaths from infection at a given time. If people with virulent infection, if there's a lot more of these, it's going to affect deaths from infection. So what's the final thing we have to do to complete this model? What do we have to specify still? Well, okay, the formula for this, and in fact, yes, we did specify mean time with infection to be 10. So the formula for this guy needs to be specified, deaths from infection. So I'm going to be clicking on this, okay? Deaths from infection, and the formula is going to be people. Now, I'll tell you a trick. So if you start typing, you do control space here, you should be able to get, hey, come on, it's not, oh, that's right, when I use this when I use this collaborate software, it kills my autocomplete. I think you folks should be able to do it. Control space or command. I think on Mac it's command space. Maybe it's command shift space. People with virulent infection divided by mean time with infection. Okay. You folks have recourse to it. I do not, because I'm writing the software to broadcast my video. I specified a formula. The formula states the value of this flow in terms of people per whatever the unit of time is, day. In terms of the things it depends on. What does it depend on? Well, it's shown with the links here. It depends on mean time with infection, depends on people with virulent infection. Okay? Does that make sense? Okay, who needs help? Who needs help? Okay? Okay. That can be either a good sign or a bad sign. It either means people are comfortable or they're beyond help. And it's disconcerting as a lecturer to see no hands go up. Okay, great. But the time is ticking, so let's run. So what do we have to do? We have to finish this model, we have to build it. Okay, so we could do model build, and that's going to make it runnable. It's going to make sure that things are hunky-dory. And in this case, you'll notice down the lower left, it said build completed successfully. So what is that telling us we can now do?
Run it.
We can run it. Okay, so we can right-click here and say run. And it will actually call up this model in a form that we can run it. So what we've done is we've specified the model declaratively. We've kind of said what this is. This is a stock. This is a flow. What's the formula for the flow? And it's taking care of the how. It's taking care of all the details of sort of how to do it. We've just specified what is in this system. We could run the model now. And what we will see is an animation. If we go double click on this, there's actually a little graph here we can show, and what it shows is this flow. This stock is draining over time. Okay, it's draining down from 1,000 people at the initial time down to 30. Where did I do that? How did I do that? Well, ladies and gentlemen, I double clicked, or actually just single click would do it, and then there's right next to this people thing. There should be a little graph, and you should be able to call that up. And in fact, you can even right click and this is preventing me from doing it because of the collaborate, I think. But you should be able to right-click and you should be able to actually copy it to for example, to paste into a spreadsheet. Okay, and you'll notice it actually shows the number of people here at a given time. And it actually states, this is the flow, the number of people dying per, say, day. I'd have to go look at what the time unit is. Okay? So we've just seen a little animation of this, right? But this has required us, and you notice it keeps on rescaling, it keeps on going back up. Let's do something a little bit more adventurous, shall we? And we can complete today's session with a triumph. Well, okay, it would at least be a good thing. Ladies and gentlemen, for the final coup de grace, let us go down here to the analysis component of the palette, and let us create a time plot. And let's drag a time plot in to here. Okay? We're dragging a time plot in, and we'll drag it out here. And this time plot will allow us to see that value so we don't have to double click and all that sort of nonsense. Okay, so I dragged in, it was down in the analysis component of the palette, which was a couple things down, and I dragged in a time plot. And down here, I need to specify some information. So I'll say, plot stock, I'll give it a nice name. And then I'm going to add a data item to it. And what do I want to plot, ladies and gentlemen? None other than the value of the stock. And so I need to go up and check the name. You folks will, again, enjoy recourse to autocomplete, but my system is trapped and unable to afford me those services. So I'm just going to type it out. People with virulent infection. So again, what did I do? I dragged in the time plot to main. I went and I did add new data item, and I typed in people with virulent infection. Ladies and gentlemen, build it. And shall we run it? Okay, so we're gonna run it, and now we have a situation where we have a time plot associated with that stock, and we don't need to depend on the vagaries of clicking here and having a rescale, and it's plotting out over time. You'll notice that it's not going as fast as it can. There it is, and wow, there's very few people with virulent infection now. So this exposes the limits of continuous approximation to count of people. Here we have 10 to the minus 115 persons left, which is not even a sliver of a fingernail remaining. So what we've just done is we've declaratively specified a system here in terms of stocks and flows. We've specified the requisite information in terms of an initial value for the stock. We specify the system structure. Remember, structure determines behavior. That behavior we saw, that's all coming out of that system structure. And we could have used different values for initial number of people. We could have used different values for that basic parameter, the length of time. But we would have still seen that basic behavior come out of it. Okay, declining exponential. There's a negative feedback loop here, and it was declining. So we specified this. We specified the initial value. We specified the formula, and we used the auxiliary variable, this constant, as a nice name for a number. But it really, conceptually, the number is part of the formula. And then we specified that a time plot should plot out the value of the stock, and plot it out it did. I have one final quiz for you. One final query here. One final challenge. Ladies and gentlemen, what we saw, the behavior that we saw, that was characteristic of what sort of loop? What sort of feedback loop?
Exponential decay.
Exponential decay is characteristic of what sort of loop? Negative feedback loop. Can anyone identify for me the negative feedback loop in this diagram? The answer was blowing not in the wind, but in a slide I gave earlier. But I'm asking you to identify, where is there a negative feedback? The answer is also indicated, it's related to what's on the board there. But where is there a negative feedback here?
Between people infected and people alive, or people infected and people dead?
Okay, so if we wanted to label these transition or these links here. Let us label this people with virulent infection. If that goes up, what is the polarity associated with this? If people with virulent infection goes up, if we have a larger number, to some reference value, deaths from infection will tend to go up or down compared to the value it otherwise would have had. Tend to go up, right? If we have 1,000 people instead of 0, it's going to tend to be more people who are dying from it, right? So it should be associated with a plus. And where, ladies and gentlemen, pray tell, is there a negative? Where's the negative link?
Mean time until death to deaths from
It's true. Okay, that's an astute comment. There is actually a negative here, right? The longer it is, because this is in the denominator of this flow, or at the formula associated with the flow, the bigger the mean time to infection is, the smaller will be deaths from infection. That's true. But ladies and gentlemen, that's actually not in the loop directly. That's a link here between that number and this. Where is there a loop here? This first link that we identified here, there's actually a loop with that. That's one element of a loop. Where's the other component of the loop?
Deaths from infection will
Yes.
reduce the number of people with virulent infection.
That's right. So it's actually staring me in the eye. It's this link here between the between this flow out and the stock. The flow out is decreasing the stock, just as on the board here, over here, we talked about that. So deaths from infection, if you increase deaths from infection, the rate at which people are dying, in terms, from 0 people per day to 100 people per day, will people with viral infection tend to increase or decrease compared to what it otherwise would have been? It will tend to decrease, and therefore there's a negative link conceptually from deaths from infection to people with virulent infection, and that's important. And ladies and gentlemen, oft overlooked. It is something that I referred to in some of my slides here implicitly, and I didn't want it to go missing. But when you see these links here, part of the link is through this flow. Okay. So, ladies and gentlemen, in short, there is a negative link here. And it's that negative loop here which leads to that declining behavior we just saw. That's the characteristic hallmark of a negative feedback. It's an approach to converge on some steady state, some situation where it's in balance. In this case, the balance is there's nobody with virulent infection and no deaths from it. Nothing is changing. There's no deaths. The flow is 0. The values of the stocks are in equilibrium. There's no changes in the value of the stocks because the flows are 0. Or the flows are equal in and equal out if you have both in and out. So here, ladies and gentlemen, we saw a negative feedback, and don't lose the fact that there are negative feedbacks where the flow is part of them. Okay? So that was the final challenge. With that, I will close today's lecture, and be sure to start work further on that problem set 1. Okay? And that's due February 5th.
February 6th.
6th. Thank you. 6th. Yes.
The problem set's available online, right?
It is. It's on Moodle. Yeah.
Okay.
And I updated it with a question today on units. So, yeah.
So I came to you last week and let you know about how to